Hi everyone, welcome to NASA's Goddard Space Flight Center. My name is Elizabeth and I'm the social media lead here for the Hubble Space Telescope. And we're live now with some really big news from Hubble. And here to tell us more about it, we have Dr. Jane Rigby with us, and she's a co-author of the result that we're going to be talking about, and also the operations project scientist for the recently launched James Webb Space Telescope. And we also have with us Dr. Patty Boyd, who previously worked as the Deputy Operations Project Scientist for Hubble and now works as the Chief of NASA's Exoplanets and Stellar Astrophysics Laboratory. Thank you both so much for joining me today. I'm really excited to hear about this Hubble news. And for anyone watching live, if you have questions during the stream, please feel free to comment them, and we're going to do our best to get to some at the end of the show. But for now, I think we should just jump right in. So, Patty, it sounds like Hubble just broke a pretty impressive record. Could you tell us what Hubble discovered?
Sure, I would love to, and it's really exciting to talk about this record-setting star. So, like so many other discoveries from Hubble, it starts with an image, a very beautiful image. And one of the first things that you can see in that image are galaxies. And those galaxies are actually gravitationally bound in a cluster. Those are fascinating objects in the universe. They have a huge amount of mass. And what's very special about this particular image, in addition to that beautiful cluster of galaxies, is it actually contains an image of a single star whose light left that object when the universe itself was less than 1 billion years old. So this is a rare event, and we're really excited to learn more about this object.
Yeah, that sounds super exciting. And just as a refresher for everyone, Hubble has been orbiting Earth for almost 32 years and is still generating incredible science like we just heard about. So Patty, could you also tell us just what can astronomers learn about our universe by examining this star?
So when we look at the stars in our own neighborhood, like when you look up at the night sky, those stars are in our Milky Way galaxy. They're in the same galaxy that we're in. We're a star, one of 100 billion or more in the Milky Way. And those stars evolved a lot like we did in this same Milky Way galaxy. And they're about, thousands of light years away from us when we look at them. So the light from those stars is coming to us thousands of years later. When we're looking at this star called Earendel, we're looking at the universe itself when it was like in its first billion years. We're at 3.8 billion years now. The universe has changed a lot in that time. So Earendel is this rare window when we can actually look back and see how stars were working in those very early days of the universe.
Wow, that's very interesting. Thank you. And another cool part about this observation is that it was only possible because of an astrophysical phenomenon known as gravitational lensing. So Jane, can you kind of break down for us like what gravitational lensing is?
Sure. So we can see this star, even though we're looking back so far in time, because of two things. One, the speed of light's not that fast, right? So we're able, as Patty was saying, we look back in space to look back in time. And the other is this phenomenon of gravitational lensing, which is just the fact predicted by Einstein that mass bends space. And so light is traveling through a curved space-time, and so it acts like mass is bending light, gravity is bending light. Well, if you think about it, what happens when you're bending light? Well, eyeglasses are bending light, right? They're getting the light to change where it shows up in your eyeball so you can see better. So it turns out that this phenomenon of gravitational lensing, when you get big concentrations of mass, either a galaxy or better yet, a cluster of galaxies together, they can act like a cosmic telescope and bend the light, focus it toward, accidentally, toward us. And so this is a really rare phenomenon. About maybe 1 in 1,000 to 1 in 10,000 galaxies are gravitationally lensed. But when this happens, we can take advantage of these cosmic telescopes and then observe them with our human-built telescopes to see way farther than we normally can. And those background galaxies, they're way behind the cluster. They don't have anything to do with the cluster. We see them not only much brighter than they really are, but stretched and magnified, kind of like they're in a funhouse mirror. And that lets us study them in greater detail than we normally can with our current telescopes.
Okay, gotcha. That's really cool. And so another thing I'm wondering, like, how did astronomers, when they were making this observation, know that Earendel was an individual star rather than a bigger cosmic object?
Sure. So this is a cool case where this is a discovery that was half on purpose, half, oh wow, that's cool, which is how a lot of science works. So the cluster and the lens galaxy were found in 2016 by Dan Coe and collaborators. And so they found the arc and said, okay, that's a very high redshift arc, redshift 6, a lens galaxy at redshift 6, about 1 billion years after the Big Bang is how we see it. And so, and then Brian Welch, a graduate student at Johns Hopkins, was given the task of modeling this thing and doing the lens model of where's all the mass in the cluster and getting that to reproduce the distorted shapes that we see of the lens galaxies. And as he was doing this, there's this dot in the middle of the lens galaxy. And try as he could, that dot had to be really small in all the models, like super small, like the size of our solar system. And the magnification had to be really high, like thousands. And so the most obvious explanation is that we're seeing either one star or maybe a couple stars, but it's not like a big star cluster, but we're seeing down to the scales of individual star or multiple stars all the way out 1 billion years after the Big Bang.
Okay, wow. And speaking of, this star being within the first billion years of the Big Bang, Patty, how did astronomers know that about this star? How did they know it was in there?
That's a great question. And so, like many of the images that Hubble takes of these fields, these treasury fields, we're observing them to collect as much data as not only the team wants to get the science that they want to get out, but that the entire community can really mine that rich archive and get a lot of science out. So one of the ways you can get the most science out of an image like this is to observe it in multiple filters. And the filters are basically different colors of light. So they specify a certain range of colors. And so this is a multicolor image using 2 instruments on the telescope. And what that allows us to do is, for the galaxies, each galaxy is going to have a certain brightness in those filters. And we can look at how that brightness changes as a function of our filter. And what we see with these objects that are very far, they're red-shifted. We call it red-shifted. As they move further from us, the whole universe is actually expanding. The light gets shifted into the red. And what that will do to a galaxy's spectrum that's far red-shifted is it'll actually kind of block it out in the optical. You won't see the light there. It'll just start to peak out the redder and redder that filter gets. So if you notice in the image that smear that we're looking at, the sunrise arc it's called, it's very red compared to the rest of the image. And that's why, is the light's just starting to pick up as we go redder. And you can use that to estimate its redshift. And that is exactly how the objects in that arc are estimated. They're all at about the same redshift of 6.2. And you use that number and the photometric information that you have to estimate everything else. Its distance and then its size scale is related to that. So there's just a tremendous amount of scientific information in these multicolor images, in addition to just the beauty of looking at the galaxies that are in them.
Oh yeah, for sure. And Patty, also, why is it important to be studying this star that is within the first billion years of the Big Bang?
So when we look around at our local universe or the stars in our own galaxy, we get a picture of how the universe has evolved. And one of the coolest stories about that is where matter came from, where the heavy elements came from, where the carbon, calcium, oxygen that makes up everything, our bodies, our bones, our telescopes, where did those elements come from? And the answer is that they're fused in the centers, in the cores of stars. And massive stars in particular are very efficient at this. They fuse lower elements like hydrogen and helium into heavier elements, and then they explode in supernova explosions, and they spew that material out into their local environment so the next generation of stars can pull that in as they're forming. Those are the kind of things that form rocky planets like the Earth, where we've got like an iron core and all those elements in our atmospheres. Those were fused in earlier generations of stars. So Arendelle is this single star, the farthest yet that we've been able to observe, and it will allow us to see how that process started to be put together in the very earliest days. When did those very early heavy elements start to be infused into the material? And it's just a window that's opening up onto the next big thing, because that light is pushed so far into the red that we need a telescope that can go even further into the red than Hubble can to really uncover the cool things.
Yeah, and speaking of, I think another fantastic part about all of this is that there's already approved observations to look at Arendelle with the recently launched James Webb Space Telescope, which is a super powerful infrared space telescope that just launched in December. We're so excited for it to begin science operations this summer. And Jane, could you kind of tell us how Webb might bring this Hubble discovery even farther?
Sure. So I learned about this lens star when the discoverers came to me, said, so do you want to be, we're trying to figure out how to plan some Webb observations. Are you in? I'm like, oh, I'm totally in. That's cool. So what we worked out was a set of observations with NIRCam, which is the near-infrared imager, to get colors in all of those filters that are too red for Hubble to do well, right, or to do at all, right? And so Webb will pick up where Hubble left off getting redder filters. So we'll have very crisp, gorgeous images. We've already proven with Webb that we can take gorgeous images. It has a very, very sharp telescope. And now we're getting the science instruments ready to go. The second science instrument that we will target for this galaxy and star is NIRSPEC, the near-infrared spectrograph. And so we'll be taking spectra of not only the lensed galaxy, the sunrise arc, but also the star Arundel. And so the NIRSPEC has a lot of cool bells and whistles. One of them is it has this microshutter array that has 250,000 doors that can open and close magnetically. And so we'll open up doors, we'll close most of them so we don't get the brightness of the sky in the way. And then we'll just open some doors for the lens galaxy and for Arundel the star. And we'll be getting spectra, right, with a little prism to tell us about what's inside that galaxy. What is the temperature of that star? How bright is it really? How, as Patty was talking about, how much of the heavier elements that were made in stars are in this galaxy versus just the boring hydrogen and helium that's made in the Big Bang.
Okay, gotcha. And so more broadly speaking, why is it important that both Hubble and Webb are going to be operating at the same time?
Sure, so Hubble and Webb are really complementary. They're not really in competition. When we built Webb, we knew full well there was a Hubble up there doing great stuff, and we didn't try to replicate that functionality. So it's really like players in a band. Like, you know, your drummer and your keyboardist are doing different things. And so you select them for different skills. So Webb is really designed to do the things that Hubble can't. It has much greater spectroscopic capabilities than Hubble, so we can really see what the universe is made of, which is great because that's part of what my research is. I love spectroscopy. What's stuff made of? And then the other part is that we're operating in the infrared with Webb. So we're looking, the bluest light that Webb can see is like a dusky red, like red wine. And then it just gets redder from there, right? So whereas Hubble can see into the near infrared, and then it can see pretty hard into the ultraviolet, like bluer than cats or bees can see.
Okay, yeah. It's going to be really great. I'm very excited for them both to be working together up there. And back to Hubble, Patty, could you just sort of tell us how Hubble's doing these days? How long we can expect it to last?
Sure, absolutely. So Hubble is actually doing great. And it was launched in 1990, so it's coming up on its 32nd birthday in space. That is a long time for an observatory to be in space. It's in a low Earth orbit, and its orbit was chosen so that it could be rendezvoused with the space shuttle. And astronauts could actually grab it and bring it back into the bay there and service it. What servicing meant was that it could refurbish the instruments, refurbish the computer, the power systems, and this was done 5 times during the lifetime of Hubble. During the last servicing mission, the astronauts worked very hard to leave the telescope at the peak of its capabilities. And ever since then, there's been a team of engineers and scientists working together on the ground to extend the lifetime as much as possible. So we're expecting Hubble to continue into the next decade so that we can squeeze as much great science out of Hubble as possible.
That's fantastic. Thank you, guys. All right, so bear with me for a second. We've been getting some questions from social media, so let's see if there's anything we can talk about here. Okay, so we did talk about this a little bit earlier, but maybe, Patty, if you want to go into this a little bit more. Someone on YouTube is just curious, more knowing about how we can tell this is a star rather than, you know, a galaxy, basically. Or Jane, if you want to take that one on,
Sure,
either way.
I can take that one.
Okay.
So the main constraint that it has to be really small. So the main constraint is that it's really small and really bright. And so the size constraint comes mostly from the fact that in the images, it looks like a dot. It's round. It isn't stretched. And if it had any significant size, like bigger than the size of our solar system, then given the really high magnification, we would see it stretched. But we don't. We see it as a dot. And so that places a really strict limit on the size. In the paper, we give it in terms of, but they're all about the size of the solar system. So it's got to be smaller than like out to Pluto, right? So that's one constraint. It's got to be something that fits in a small box. Okay. And given that really high magnification, something like thousands, and whether it's 1,000 or 10,000, we showed a bunch of different models to show that it's somewhere in that range, okay? So you have something that's given its brightness and magnified by factors of 1,000, well, that's like 1,000,000 times the mass of the sun, 1,000,000 times the luminosity, the brightness of the sun, okay? So, all right, what is out there that is bright as a million suns and fits in our solar system? Well, that's really very massive stars, or binaries, could be binary, or it could be a accreting black hole. But we also know it hasn't changed in brightness. So we have observations. Hubble has observed this star multiple times, in part to look for supernova, to look for lensed exploding stars. And in those multiple epochs, we don't see any sign that it's changed brightness. So one of the characteristic features of accreting black holes is that they go up and down in brightness and they change. And so we think the most likely explanation in the paper is that this really is a massive star.
Yeah, okay, makes sense. Thank you. Awesome. Well, thank you all so much for sending in these questions on social media. I think we are unfortunately running out of time for today, though, so we're going to have to wrap things up. But thank you all for tuning in to learn more about Hubble's discovery of the farthest individual star ever seen. This is a really cool story, so if you want to find out more, be sure to check out nasa.gov/Hubble. And as always, you can keep up with Hubble on social media at NASA Hubble on Facebook, Twitter, and Instagram. Thank you all so much for joining us today, and have a great weekend. Bye, everyone.